we'll move on to the next problem. We're halfway through now. So we have, so these problems are all from a Vietnamese, basically website. I think it's a contest that was in 2011 and 2012, and also 2014 and 2015. So we have a circle passing through the vertices B and C of triangle ABC, and it intersects the sides at E and F. All right. So it intersects CA at E and AB at F. And then BE meets CF at G. And then M and N are the reflections of A over E and F. All right. So let me use my reflect tool. This is M, and this is N. So EF is like a mid-segment of triangle AMN, it looks like. P, so the reflection is C and B over AG. Okay, so we got to draw the line AG, and then we reflect C and B over it. I'm not sure if the one for C will lie on the page, but let's see. No, it doesn't lie on the page. There we go. So this, so this is P, this is Q. Yeah, maybe this will be another isogonal conjugates problem. Through the circumcircles of BPM and CQN are the same size. That doesn't look right. Hold on a sec. Maybe I switched E and F or something. E and F. BE meets CF at G. The reflection of A. Okay. P. Q are the reflections of. Oh, yeah, I did. I swapped P and Q. So this should be P, and this should be Q. And then I want to draw the circumcircles of BPM and CPQ. And it's saying that these circles have the same size, which is kind of interesting. Let me make it clear that these are reflections. So yeah, I think it looks clear from the figure that these are reflections, right? So I'm going to just draw this point, and all right. Kind of interesting. These circles always have the same size. Whoops. I mean, basically that means D has the same power with respect to both circles. And basically, yeah, that means that AG is the radical axis of those two circles, right? So A has the same power. Is that obvious? So the power of A with respect to both circles is BMNC cyclic. I guess we want to show BMNC is cyclic. And that's obvious by power of a point, right? I think this might be an easy problem. So BMNC is cyclic. And so A has the same power with respect to both circles. And can we show G also has the same power? How would we do that? So we know, it's kind of interesting. We want to show G has the same power with respect to those two circles. Maybe we could label this point and this point, and we could try to show BJIC is cyclic. Because that would do it. Okay. So we want to show BJIC is cyclic. You know that angle JBC is equal to angle EFC. So we want to show angle EFC. Basically, we want to show EF and IJ are parallel. It's kind of interesting. We want to show EF and IJ are parallel. So if we can show like GF over GI is GE over GJ. So wait, does that mean FEIJ is cyclic? No. No, we want to show they're parallel. Oh, if we show EF and IJ are parallel, that would show. So since we know EF is parallel to BC, I'm sorry, we know BFEC is cyclic by power of a point. If IJ was parallel to EF, that would mean that BJIC is also cyclic. But by an angle chase. And once we know BJIC is cyclic, that means G has the same power with respect to the two circles. So we haven't used that P and Q are the reflections. But basically that means that GP is equal to GC. I mean, we know that GP is equal to GC, so it's basically, I mean, there's a bunch of equivalent ways to think about this. Oh, so once we know that AG is the radical axis, basically we know that H and D lie on that radical axis, and so where H is like the midpoint. Yeah, I forgot. So yeah, how does that prove they have the same size? So yeah, if H is the midpoint of PC and D is the midpoint of PQ, and they both have the same powers, I guess if the radical axis is like halfway between the two circles, then yeah, okay.
I guess we can try proving that angle PMB is equal to angle QNC.
BMP is equal to QNC. All right. So yeah, I want to show, yeah, G. G has the same powers. All right. So we know AP equals AC and GP equals GC. I feel like we're close. I mean, yeah, if A has the same power with respect to both circles, and yeah, we want to show A is the same distance from the centers of the two circles. There's so many equivalent ways of thinking about this problem, so it makes it tricky. But we know BPQC is cyclic. I don't know if that helps. It's an isosceles trapezoid. So BP, okay, if we know BPQC is cyclic, then we know that BPQC and you just don't know that G lies on this line. That's the thing. Yeah, how do we show G lies on the radical axis of those circles?
One thing you might look is GJ. I think GJ into BG is if we prove is equal to GI into GC, then that would be a good that would be a good approach, and that reduces to BJIC being cyclic.
Yeah, if we can show BJIC as cyclic, that would solve the problem.
Yeah.
But maybe, oh yeah. I wonder, are EF and yeah. see. Okay, so yeah, we have to use the fact that these concur. I don't know if we've used the fact that they concur yet.
What you figured out about the below cyclic quadrilateral, below quadrilateral BP CQ?
BPCQ is an isosceles
Yeah.
traploid. So yeah, we know it's cyclic. Yeah, we just have to show G. So what is G? G is the intersection of BE and CF.
Can we try completing the quadrilateral BFEC?
What?
Completing BFEC, I mean extend FE and BC to meet at some point.
Yeah, because that would help with like projected geometry, right?
And maybe this point and M and N are collinear. No, wait.
Yeah. But it looks collinear with J and E. But is that just the?
Yeah, that's just a coincidence.
Yeah, that was just a coincidence. We have to use that these concur. That's the trick. So, but let me see. Often it helps to do this. Actually, let me do it like this. So, let's see. Oh,
Isn't it obvious that AD is the radical axis?
Not yet. So I know A lies on the radical axis. I can show the line through A, H, and D lies on the radical axis. I just don't know that G lies on that line. So I know A, H, and D are collinear. But I don't know that G lies on that line. That's the thing.
Oh.
Is GM equal to GN? That's a good question. No. It's close, but yeah, if I move the diagram around, it's actually hard to make it that different. But yeah, you can see here that GM isn't equal to GN. Yeah, so I can show A, H, and D lie on the radical axis. But I can't show that. I still have to show that G lies on that line. But wait, P and Q are the reflection. Wait.
Don't we know that AGH is collinear because P is the reflection of C over AG?
Yeah, I know. Actually, we do know. Now I'm confused what it is I'm confused about. So I think we might just have proved it. I think it might. So we can show A has the same power with respect to those two circles. So A lies on the radical axis. And G so yeah, and then AG is perpendicular to PC. Yeah, I'm a little confused here. So it might be obvious. I'm just trying to figure out how. Okay, yeah, no, I don't know that, I know A lies on the radical axis, and I know that these 4 points are collinear, but I don't know that that's the radical axis. So yeah, if that makes sense.
We can extend AD, I mean, mark the intersection of PB and QC.
Okay, one sec.
We know by symmetry that it would lie on AD.
Wait, so draw BQ, draw line BQ, you said?
Now I said PB and QC.
BP and QC.
Yeah. We know by symmetry that this should lie on AD and these powers are equal.
Okay, because A has the same power with respect to both circles. So
And
wait,
now,
how do we? Okay, I think that does it. I think you're right. Yeah. So
And I found out that we could use signed rule to completely simplify this, because we know that there are two triangles involved, PBM and CQN, I guess. So these two triangles have one common side, that is PB and QC, which are equal because of the isosceles trapezoid. So by signed rule, the angle opposite to PB, that is M, that is angle M by PB, must be equal to QC, and opposite to that is angle N. And I found out that they are equal.
how did you find that they're equal?
Yeah. Yeah. Yes. Yeah, it's a pretty complicated figure. I'll get back to you in 5 minutes.
Okay, that's all right. Okay, so yeah, by symmetry, AG, PQ, and PB and CQ concur at a point K. And that point K, we know lies on the radical axis by symmetry, because KB times KP. And so since A is also on the radical axis, this whole line is the radical axis. And then okay, I'm just thinking through. Now, once we know that all those points lie on the radical axis, since it's halfway between the circles, then we're saying they have to have the same size. Yes. Okay. So I'm just trying to think. So I'll try to. First, I'm going to show AK as the radical axis. So I'm going to write this up. Whoops. Sorry about that. Let me delete a few of the things I added, and then I'm going to add it back in. You don't need I and J, I don't think, right? Okay. So shrink it just to make more room. Okay, so first we want to show BFEC is cyclic. And that's true by power of a point. Whoops. So, oh no, we know BFEC is cyclic. We want to show BMNC is cyclic. So, AF times AB is equal to AE times AC. And then that implies 2AF times AB is equal to 2AE times AC. And that means that AM times AB is equal to AN times AC. All right. And that means that BMNC is cyclic. Oh, what happened there? Let's try that. Here we go. Okay, so then we know BMNC is cyclic. Now so actually, this means that since AM actually, we don't even really need to say that it's cyclic. We could just say A lies on the radical axis of those two circles. All right. What? Oh yeah, that is what I wanted. Okay, so A lies on the radical axis of those two circles. And then we have CPBQ as an isosceles trapezoid. Okay. Yeah, any trapezoid, any quadrilateral that has a line of symmetry is an isosceles trapezoid. So that means CPBQ is cyclic. Well, we don't even need that it's cyclic. Basically, just by symmetry, BPCQ and AG concur. So I'm going to let it concur at a point showing I. Okay. And then I has the same power with respect to those circles. So right. Okay. And so AI is the radical axis of those two circles.
Could you explain the collinear part between AG, CQ, and BP? I was scratching my head on something else.
Oh, so basically P is a reflection of C over AG, and B is a reflection of Q over AG. So I mean, P
B
and
is
C
the
are
reflection of. Oh, got it.
yeah, and the problem statement P is a reflection of C
Yes,
over AG.
yes.
So yeah, by symmetry, those have to concur. So AI has to be the radical axis of those two circles. And so do we even need D and H? Because now we know that, yeah, once we know that AI is the radical axis. Wait, where did
Right.
we,
It's the trapezoid was the important piece.
yeah, do we even need that G is the intersection of those three? Okay, I'm trying to figure it out from here. So yeah, where do we how do we finish it off?
Let n dash be the point such that n dash is parallel to PC. Then we show that we basically reflect n over the line AI.
Okay, hold on one sec. So did you say n dash is parallel to BC?
PC.
PC. Okay.
Yeah, and n dash is the point on the circle closer to A.
Okay.
Yeah, this one. Now we know that AJ times AP is equal to AN times AC, which is equal to AM times MB. So AJP have to be collinear.
Okay. So AN times, so say that again. So AN times AC
Is AM times AB.
is AM times AB.
Yeah.
And that's equal to
Power of A. So we see that power of A is equal to AJ times AP. So AJP have to be collinear.
So I think that
we can also let J be the point where AP intersects the circle, and then try proving that J is the reflection of N. Once we prove that J is the reflection of N, then CQN is basically reflected to BPJ. So both should have similar radii.
Okay, I'm going to do it the other way. So
yeah. Now we want to show that J is the reflection of
N.
N.
So AN times AC is AM times AB, which is
which
AJ
is
times.
AJ times AP. So yeah, AJ is equal to AN.
So AJ is equal to AN, right?
And we also know that AI bisects angle JAN.
Okay, so
This implies that J is the reflection of N, and hence both should have similar radii.
okay, so I can see why J is the reflection of N. Then where do we go? Oh, and B is also the reflection of Q, basically.
Yeah, basically we reflect triangle CQN to PBJ. So the circle should also be reflected.
What I'm kind of wondering is, did we even need G to be the intersection of CF and BE? Like, could G have been any point? Like, what if G was like any point? Would the problem still be true? See what I'm saying?
Yeah, we can try moving that. But if we are reflecting over G, means it G has to be something.
So yeah, I'm gonna finish writing up the solution, but I wonder if G could be any point. Like, does G even have to be the intersection of BE and CF? I don't think it does. So I'll say, I'll just finish writing it up as you said, but let AP J. So then, what is it? AJ times AP. And then AC equals, since AC equals AP, AJ equals AN. Um, and so that means so J, P, and B are the reflections of C, N, and Q over A, G.
But wait, how did we prove that it's an isosceles trapezoid in the first place?
Oh, one sec.
That should be dependent upon G, and we didn't use it.
So yeah, so if you start with points, so we started with points B and C. If you reflect them over the line AG and you get Q and P, if you take any 2 points and you reflect them both over a line, you get an isosceles trapezoid, right? Like if I pick a random line and I have some random 2 points, this and this, and I reflect them both, then this is an isosceles trapezoid, right? O prime R prime, right? By symmetry. Or does that kind of make sense?
But what line are you talking about?
AG, because P and Q are the
Oh,
reflections.
it's given. Okay.
Yeah. So, but yeah. So this is the proof. So if those are all reflections, then those two circles have to have the same size, right? Okay. But I'm going to check if G could have been any point. So I'm going to open up a new window. Just do this really quickly. As fast as I can. Pick any point. Circle. And I draw this line. And then I reflect B and C over it. Let's see. That might be off the page. Okay. And then what did I do after that? Then I BPM. Oh, I did another reflection. That's right. Then I draw the circles. Let's see. Yeah, G could have been any point. These circles look like they're always the same size, right? That was irrelevant. It didn't have to be the intersection. Okay. C, doesn't C have to be on that circle? I guess, yeah, BFEC has to be cyclic, but G doesn't have to be the intersection of BE and CF. Like G, we didn't have to define G to be the intersection of BE and CF. G could be any point that we want as long as BFEC is cyclic, is basically what I'm saying. All right, so I'm going to move. So yeah, the problem just had an extra condition that we don't need. All right, so I'm going to go on to the next one. So ABC is a triangle with altitudes B, E, and CF. M is the midpoint of B. I'm going to draw M first. I'm going to draw the altitudes. B, E, and CF. N is the intersection of AM and EF. That's N. Whoops. X is the projection of N onto BC. All right. X looks like projective geometry might be handy. And then we project X onto AB and AC. Y and Z. And we want to show that N is the orthocenter of AYZ. All right. Whoops, I think I fixed some of this up. All right. Y, this should be Y. And this should be Z. Oops. All right. So how do we show N is the orthocenter of AYZ? Let's see. So if we could show YN is, this looks kind of like projective geometry. We want to show YN is parallel to BE. So if we project through F, Um, let's see. What if we project A, F, Y, and B through N onto BE? So A goes to G, F goes to E, Y we want to show goes to the point at infinity, and B stays at B. Okay, so, sorry, one sec. So, I'm just thinking through this. Obviously, A, Y, X, Z is cyclic. Yeah, so this feels like projected geometry. Let me just see for a sec. Yeah, I think this is just projected geometry. So, but yeah, we would need BY over AY. So, trying to think how we would get that. Yeah, maybe there's a better way to think about this. I wonder if AX is the median. Yeah, AX is the median. Well, yeah, if we can show Fn over Ne is Fy. Yeah, if we could, okay, I think there's an easier way to solve it. So Fn over Ne, we want to show is By over Yf, but By over Yf is Bx over Xc. So we want to show Bx over Xc. We want to show N and M are corresponding points. And that's true if AX is the median. Okay, so yeah, I feel like this is an easy problem. I'm just kind of overthinking it, but like, can we show that AM and AX are orthogonal? So AX is a median. Are I and H orthogonal or? Okay, let me try. Okay, so we want to show Fn over Ne is Cx over Xb. I'm trying to use projective. Because Fn and E project to B, N, and C. Yeah, let me do it like this. So we know Fn, E, and J are in harmonic conjugation, right? So that means B, M, C, and J are in harmonic conjugation. So basically, BJ is equal to BC, right? No. What am I thinking? Oh, no, because that's not a point of concurrency. Never mind. But this looks a lot like, this looks a lot like the proof of Blanchett's theorem. So is what's the angle bisector of BNC? Oops. Right? I mean, this feels like it should be easy. I'm just struggling with it.
Is
So
AN perpendicular to EF?
is AN, no. So I can show that XN bisects angle FXE. So angle XFN is equal to angle, wait, is that true? I thought it was. Oh, wait a sec. Maybe not. Let me draw the midpoint of EF. So J and M are corresponding. I want to show that N and X are corresponding. And I know that MJ, I feel like I've done this before. This looks really familiar. So, I mean, I just want to show AJ and X are collinear, right? And I know MJ is perpendicular to EF. So AJ and AM are isogonal, right? Because they're corresponding points in similar triangles. I just need to show X applies on that. I just need to show AJ and X are collinear. It feels like it should be really easy, right? AJ and X are collinear. You guys gotta know this. Oh, if we can show
ये लगा
all right, let's see. So if we can show the cross ratio FJNE is equal to BXMC, that would solve it. But I don't know if that really makes it easier.
पीछे पर खटोले के नीचे
What?
I'm sorry, my mic wasn't.
Oh, it's all right. Yeah, so if we can show JNMX is cyclic, that would solve it. Oh, but I think that's okay. So I think this is it because NXM is 90 and NJM is 90 because that's the line from the center of the circle to the midpoint of the chord. So yeah, I think this should do it. So we know that that's cyclic, and then an angle chase because we know AJ and AM are isogonal. That should do it, I think. Just thinking how to write that out formally. So once we know that's cyclic, angle MAC is equal to yeah, if M corresponds to J, then I think N has to correspond to X. I'm just trying to think why. So AJM is similar to I mean ANJ, because J is a midpoint, so AJM should be similar to ANX. Well, this looks a lot like the first problem I did on the Christmas special mock geometry Olympiad, where I had this kind of a thing. I have to show that Fn over Ne is Cx over Xb. Let's see, can I show? Can I show ANF is equal to AXM? I feel like I'm close on this, but I'm just stuck. So F, N, and E project to B, M, and C. Yeah, I'm just thinking about different ways to do this in my head. You guys want me to move on to the next problem? I feel like I'm just stuck on this, and I don't know. I feel like it shouldn't be that hard, but what do you guys think?
Yeah, 2 more minutes.
Okay. So I think YZ is perpendicular to AM actually. Let's see. Is that obvious? Yeah.
So I was thinking of proving AJX collinear. Uh, so, so if we deduce something, then that cyclic quadrilateral you found out J and XM can be useful. If you could you draw AJ and JX?
Yeah, if we can show
So
their
if we
collinear, that solves it. Well,
yeah, that 180 degree in angle sum. So XJM is equals to maybe extend EF and BC.
Yeah, let me try that. So if I extend EF and
Does that
BC,
do? EF, BC.
so basically if I project EF, J, and L, then I get BM, C, and L. Or I want to show that would be the same as BX, C, and L. So yeah, EF. There's another way I could try this. So I mean I know AY ZX is cyclic, and
Okay, if we prove ANX similar to triangle AJM, then we are done.
okay.
Is there any way? I just want to prove angle ANX equals to angle AJM. That will solve it.
Let's see. EF and BC. That's right. AJ and BC. Okay. So if I define X instead to be the intersection of AJ and BC, I could try to show J and XM is cyclic. Actually, yeah, that has to be true. So that solves it pretty much. So yeah, okay. So hold on just a second. So if J and M are the midpoints, and I let J meet BC at X and AM meet EF at N, then since EF and BC are anti-parallel, actually I could just say since angle AJN equals angle AMX, JNXM is cyclic. Okay, so yeah. So here's how I'll do it. All right, I'm going to hide Y and Z for now. But basically, I'm going to say okay. Let J be the midpoint of EF. Let AJ meet BC at X prime. Okay. So we have AFE is similar to ACD, and J corresponds to M. So that means that angle AJN equals angle AMX prime. So that means that JNMX prime is cyclic. And that means that angle NX prime M, so NX prime M equals angle NJM equals 90. And so that means that x prime equals x. Okay. So now we can draw in some of the rest of the figure. What was it? Okay. So x prime equals x. And once we know that, then we have Fj over Je, or I'm sorry, we have Fn over Ne is equal to Cx over Xb, which is equal to By over Yf. Right. Because well, so I should say N corresponds to F. So since J corresponds to M, that means that N corresponds to X. So I'll say this. So to AM, so that means that X corresponds to N in those similar triangles. And so that's where we get this first ratio, Fn over Ne is equal to Cx over Xb. Okay, so this means that, oh, this should be Yf over By. And so that means Yn is parallel to Be, which means that Yn is perpendicular to Az. And then similarly, Zn is perpendicular to Ay. So that means that N is the orthocenter of triangle AYZ. All right, thanks for encouraging me to stick with this. And yeah, I'm glad we solved it. So I will move to the next one. Let's see if we can solve this super quick. So we have a triangle ABC. It's in a circle O. I'm going to draw this as fast as I can. All right, whoops. Sometimes when I do it fast, it's slower because of mistakes I make. So we have a line through the orthocenter H. So and it meets the circle at P and Q. I feel like often Pascal's theorem is useful for these kind of configurations. So P and Q. Actually, now that I see what we have to prove, I think Pascal's theorem might be really useful. Okay, so the lines through P and Q that are perpendicular to AP and AQ, they meet BC, so they intersect on the circle, but they meet BC at M and N. So this should be like the antipode of A. and these are at M and N. Okay. All right. Prove that the line through P perpendicular to OM and the line through Q perpendicular to ON meet on the circle. Okay, this really looks like Pascal's, right? Okay. So this will just draw that in, draw that in, hide some stuff. So I want to show those two things, PE and QF, intersect on the circle. So I mean, that's really the same as saying that the angle between PE and QF is equal to angle P to Q. Suffices to show that MNOD is cyclic. And wait, so I'm trying to figure out okay, because by angle chase, the angle between PE and QF is 180 minus MON. Yeah, so yeah. And then MOND, how do we show that's cyclic? Is that just like Rhimes' theorem? Okay.
Good night, Michael. I got to go for dinner right now. Bye.
All right. Thanks for joining. Have a good meal. All right. So AO and D are collinear. I can draw that in. And okay, so we want to show angle MOD is 90 degrees. Whoops. Okay. Sorry, that's my phone. Is MON similar to APQ? It looks like it. Well, yeah, that would be true if the problem were true, I think. Yeah. So maybe it's just like a homothency. So H. It feels sort of like a homothency, but not quite. It's like a spiral similarity, right? Okay, what if we do this? So like we draw like the antipode of P. So we want to show okay. like we want to show the quadrilateral GPAQ is similar to DMON. Yeah, we haven't used, how do we use that it passes through H? So we want to use that fact. So AH and AO are isogonal, right? Okay, I think, so often it helps to kind of do this. So if I let BH hit the circle at a point, I'm kind of thinking how to use Pascal's theorem here. Yeah, okay, so we want to, let me erase some stuff. I feel like I've added too much. We want to show MONB is cyclic. Let me draw that circle because it might be helpful just seeing what it looks like. So it looks like PE, I mean, we can kind of get rid of points E and F, but yeah. Yeah, we need to use that H as the orthocenter. So basically, this is like the spiral similarity point of those two. Yeah, let me hide E and F. Yeah, they're perspective. Yeah, disargs. All right. So AQ. Yeah, let's try disargs here. This is going to be a little tricky. I'm not sure how much that would help. Yeah, I think so. The intersection. I mean, a spiral similarity centered at G, we want to show takes triangle. We know it takes MN to PQ, so we know GMN is similar to GPQ. We want to show, so we know GMN is similar to GPQ, right? So what does H correspond to? So if AH is perpendicular to MN, what if we draw the perpendicular from A to PQ? Those. Or from O to PQ. G is the intersection of the circles DMN and yeah, it's like kind of like we assumed Yeah, the problem is already true. Yeah, so if we don't know yet that O lies on the circle, we can define G to be the intersection of the circumcircles of DMN and DPQ. So basically, we want to show DO and DA are isogonal. I don't know if GO and GA. Does O correspond to A? So yeah, O would correspond to A in that spiral similarity. Yeah. So if we could show DOA is similar to DM, if we could show GOA is similar to GMP, but we don't know O lies on the circle yet. So if I get rid of the circle, can we show GOA? Oh, so that means MGP is isosceles. Huh. So MGP is isosceles. I guess we missed that. And NGQ is isosceles. Is that obvious? So basically that means OM is perpendicular to GP. You need to find O to be the intersection of DA and yeah, so that might be a good way to go. Whoops. So yeah, we're almost running out of time here, but I feel like we're close to getting something. So I just want to finish up this idea. So let me hide OM. How do we know that O corresponds to A? Oh, because angle GMO is equal to angle PGA. Is that why? MPO. Yeah, so now we know O corresponds to A. Yeah. And yeah, so I'm going to delete GP. Yeah, can we show that O is the center of the circle? So if yeah, we have so much information here. GM is equal to, we want to show GM is equal to MP. So yeah, angle MOG is equal to angle MOD yeah, so all right. I feel like we're really, really close, but I'm going to stop here just because we're running out of time. So for those of you watching on YouTube, see if you can finish off what we've done. And thanks everyone for participating. And have a good rest of your day. Thanks.